Welcome to The Explainer. Today, we're diving into a research paper that shows how a really clever technique is just completely unlocking the next level of AI speed and efficiency. And what's so cool is, we're talking about a fundamental shift, making these massive models run faster, not by building bigger hardware, but by writing way smarter code.
All right, so here's how we're going to break it all down. First, we'll look at the powerful AI setup that's at the heart of this whole story. Then we'll uncover this major traffic jam it's running into. After that, we'll introduce the brilliant solution, SonicMoE, dig into its key innovations, and then wrap up with some seriously impressive results. So to really get this breakthrough, we first have to get our heads around a concept called mixture of experts, or MoE for short. It's a pretty revolutionary way to build these enormous AI models without them becoming impossibly slow and clunky.
So instead of having one giant brain that's trying to know absolutely everything, MoE models use a team of specialists. Think of it like a hospital. You don't have one doctor who knows a little about everything, right? No, you have specialists, a cardiologist, a neurologist, and so on. So when a task comes in, a router, which is kind of like a manager, sends it to the few experts who are best suited to handle that specific thing.
And the process itself is really simple but incredibly powerful. The router directs the traffic, the specialists all get to work at the same time, and then all their individual insights get combined into one final intelligent answer. And this is what lets these models scale up to trillions of parameters without just grinding to a halt computationally.
Now, what's really fascinating here is the trend. You can see that the best performing models are using more and more experts, but each one of those experts is getting smaller and more specialized. This is what we call becoming sparser, meaning you activate fewer experts at once and more fine-grained because you have more smaller specialists. And that combination, it's key to making the models better. But, and there's always a but, this push for more and more specialists has created a whole new kind of problem, a sort of digital traffic jam that's happening deep inside the GPUs that power all this AI. So what's the catch? Well, the catch is that while the actual amount of math, the computation, hasn't really grown that much, the data logistics have just exploded. We're asking the system to manage hundreds, maybe thousands of these tiny little expert teams, and all of that coordination comes with a huge hidden cost. And this is the crucial point right here. MoE models are shifting from being compute-bound to being memory-bound. The GPUs are so ridiculously fast at math now that the factory floor isn't the problem anymore. The bottleneck is now the highway, the data bus. Having thousands of tiny expert teams means you're constantly moving all these little bits of data back and forth, and it just creates this massive gridlocked traffic jam. And this chart shows you the traffic jam in action. As you can see, the more specialized, fine-grained experts we add, the more data has to get shuffled around. This input/output cost scales directly, which just means our highway gets more and more congested, and the efficiency of these super expensive GPUs just plummets. So to solve this, researchers developed SonicMoE, and this isn't just another algorithm. It's a complete redesign of how the software and the hardware work together. It's all about making the entire system smarter, not just bigger. It basically tackles the problem from 3 different angles. First, it drastically cuts down on the amount of temporary memory you need for the calculations. Second, it clears up that data traffic jam. And third, it literally stops the GPU from doing pointless work on empty data slots. It's a pretty elegant 3-pronged attack. Okay, so let's break down how it actually clears the jam. We're going to look at each of these 3 really clever optimizations one by one. First up, memory. So before, if you added more experts, you needed more memory to store all the in-between calculations. It was a straight line up. But SonicMoE found a way to compute the exact same result without needing to cache all that extra data. This keeps the memory usage completely flat, even if you add hundreds of new experts. It's a game changer. So the old way of doing things was very stop and go, super inefficient. First, you'd have to just sit there and wait for all the data to arrive from memory, and then you could start doing the math. SonicMoE, on the other hand, uses this slick technique called ping-pong scheduling. Think of it like a master chef and their assistants. While one part of the chip is busy computing a batch of data, another part is already fetching the next batch of ingredients. The processor never has to sit idle. The highway and the factory are working in perfect sync. And finally, there's the wasted work. See, GPUs are designed to work on big, uniform blocks of data.
So when an expert doesn't have a perfectly full batch, the GPU still has to run a full-size operation, and it just pads the empty space with useless calculations. It's like running a massive roller coaster with a whole bunch of empty seats. A huge, huge waste of energy and power.
SonicMoE's token rounding is this really smart system that makes sure every single roller coaster car is full before it leaves the station. It slightly and intelligently adjusts which data tokens go to which expert just to perfectly fill up every single batch. And this simple trick completely gets rid of all that wasted computation without hurting the model's performance one bit. Okay, so what does all this optimization actually get you in the real world? Well, the results are seriously impressive, and they show just how big of a deal these software-level fixes can be. First off, for a pretty common 7 billion parameter model, SonicMoE cuts down the memory needed per layer by up to 45%. That's nearly cutting the memory footprint in half, just gone. And all that efficiency, it translates directly to speed. By clearing out all those bottlenecks, it achieves a 1.86 times improvement in compute throughput on those powerful Hopper GPUs. We're talking almost twice as fast.
And you can just see the difference on this chart. For the exact same task, SonicMoE is just blowing the other methods out of the water. It's not a small incremental improvement. It's a huge leap forward in efficiency. And here it is. This is the real-world punchline. This means SonicMoE can do pretty much the same amount of work with 64 GPUs as the older method could with 96 GPUs. That's a massive 33% reduction in the hardware you need. And that translates to huge, huge savings in cost, energy, everything you need to train these powerful models. It really leaves us with a fascinating thought. While building bigger, more powerful hardware is definitely one way forward, innovations like SonicMoE prove that smarter, more efficient software can deliver just as big of a leap. It shows us that the future of AI isn't just about raw power. It's about the intelligence of the code that harnesses it. And that could fundamentally change the economics of building the next generation of AI.